Welcome to Simulation Workshop, where we learn to build worlds through equations. This session is an introduction to a series of video lectures on building simulation models using Modelica language. In today's session, we will cover what is Modelica, the history of Modelica language, then how Modelica language is different from other programming languages, and how we can model a physical phenomenon using a system of equations that can be solved using Modelica. And at the end, we will get a brief introduction to Open Modelica ecosystem, which is a free and open source development environment for building and simulating Modelica simulations. So without any delay, let's get started. If you go to the main website of Modelica language, which is modelica.org, you will be greeted with a simple explanation of what is Modelica. Modelica is an object-oriented language to model cyber-physical systems. It supports acausal connections of reusable components governed by mathematical equations to facilitate modeling from first principles. Along with this, you will have quite a lot of information about the language specification, language libraries, tools, Modelica Association, and their sponsors, and so on and so forth. But let's dissect this statement first and try to understand what really it means. So when we say it is an object-oriented language, it means that it supports the usage of classes and instances to model each component of physical systems. So this is common in many programming languages like Python, C++, Java, etc. Now it is used to model cyber physical systems. So cyber systems, we generally mean the digital control systems where we have a very clear input and where we have a clear output. And a signal from input will get processed and then will pass to the output. Whereas a physical system can be something of connected systems, like maybe two or three components are connected and they all interact between each other. So you cannot clearly state how the information flows, like which is the starting point, which is the ending point. But these are a system of connected components. For example, like if you have a component that is hot at one temperature and there is some air flowing. So whether the component is driving the phenomena or whether air is driving the phenomena or because of the heat transfer the temperature is changing, like it's difficult to interpret which is the cause and which is effect, but it all happen as a common physics phenomena. Now in engineering simulations it is very often that we'll encounter situations where a physical system is controlled by a digital controller. It can be a car where your engine control unit is defining like how the combustion should happen inside your engine. So Modelica uses acausal connections, which means like these connections does not necessarily represent an assignment operator like x is assigned the value of 1 that we do in a programming language. But this uses acausal connections where we write equations instead of assignment operations. And we use reusable components. So we have basic components already built and larger complex systems can be built as a combination of these components. So that eliminate the need of writing everything from scratch each time. So that is Modelica. Now, why do we need Modelica? There are many simulation tools already available in the industrial market. Some of the heavyweights like ANSYS, Mentor Graphics, and drawing and simulation tools like SolidWorks, which some of them are free, some of them are paid, some of them are very expensive, but they all let users perform simulations on very specific domains. For example, ANSYS Fluent let you do simulations on fluid dynamics. Mentor graphics is mainly for electronic simulations. This is for molecular dynamics. The key thing is that they all are designed for specific applications. And so the mathematical equation solving portion, they keep it hidden from the user. So user only need to know what is the problem they are solving, how to set up the problem, and then the software will take care of modeling it into mathematical equations and solving them. On the other hand, we have general purpose programming languages like C++, Python, Julia, Fortran, MATLAB, Java, Rust, etc., where you have to start everything from scratch. You have to build your own numerical algorithms, numerical schemes to solve systems instead of just sticking to the mathematical part. To bring a little more clarity, let's take how we work on building and simulating a mathematical model. So we start with a concept, then we identify what are the key parameters and relationships involved, and we come up with a set of governing principles. Once these principles are solidified, we convert them into mathematical system of equations. Then these equations are later converted into algorithms, and then the algorithms are solved for finding the unknown values. So in a typical programming language as shown here like C++ or Python, the user need to do up to this portion, that is up to defining your algorithm. That is a system of sequential operations where values are assigned from an expression to some other variables. So this process needs to be continued in an iterative manner to find the value of unknowns. Person who is working on building this model need to worry about building the mathematical equations and then converting them into an algorithm. Whereas many of these domain-specific simulation tools, we only need to reach here. The process of converting into mathematical equations will also be handled by the software. So this is very good if you are like working on very fast pace and you are solving very complex systems, but it also reduces your flexibility by prefixing the type of mathematical equations that will be used by each model. So you do not have the flexibility to control the mathematical framework of your model when you are using a specific domain specific simulation tool. So Modelica comes in between somewhere here, where Modelica allows you to write the equations that define your model, and then it will take the process of converting those equations into algorithm by itself. That way, the user can focus on building the mathematical framework of their model and be less worried about the numerical nuances of converting them to algorithm and solving a numerical process. Now, before diving deep into this process, I want to acknowledge the historical significance of Modelica and how it was introduced and how it evolved into the current phase, what it is today. The concept of a dynamic modeling language was introduced first by Dr. Hilding Elmquist in 1978 as part of his doctoral thesis. So you can find that doctoral thesis. If you're a curious reader, you can find the thesis in Lund University website or from Wikipedia. It's a pretty interesting read where he talks about the motivation for building such a language and what are the nuances, what are the fundamental concepts that are used here. So he uses computational graph theory and some of the symbolic algorithms to convert a system of connected components into a set of differential algebraic equations. After this, several parallel attempts were done by many other developers who wanted to build similar languages. But a common problem was they all were different languages and the model developed in one language was not usable by another language. So as a result, in 1996, a common language specification was proposed. That is a tool-independent modeling language where the model developed in one tool can be ported to another tool as long as they follow the Modelica language specification. By this way, it became both a modeling language and a model exchange specification. And in 2000, the Modelica Association was formed to oversee the evolving language and Modelica standard library. Now, the industrial adoption of Modelica by several commercial and open source tools also started around this time. And the Modelica Association not only oversees the Modelica part, but it also takes care of some of the industrial standards like FMI, EFMI, SSP, and DCP. To give a brief idea of like how wide this Modelica language has grown into industry simulation softwares at this point, these are just an example of some of the popular tools that use Modelica in their backend to perform simulations. So Open Modelica is a free and open source tool that we will be primarily using in these sessions. Others are mostly except for Psychos, which is a open source tool, but it is mostly abandoned at this point. There is no active development going on. But other than this, all others are like commercial tools which you need to get specific licenses, but they are like very good in lot of additional features, customized libraries. So Modelica as an ecosystem, it is growing every day, and it's a very good opportunity for every engineer to learn this language, to understand the nuances of simulation before getting into the actual industrial processes. With that, let's get back to why Modelica is so different from a conventional language like Python. So let's take a simple example and see how that can be solved using Python and then how that can be solved using Modelica. The same model we are taking, which is a simple transcendental equation, that is x minus cosine of x equal to 0, or in other words, x is equal to cosine of x. So both of these represent the same mathematical relation. And this type of equations, the complexity with this type of equation is that since the term cosine and x cannot be solved directly for x, like you cannot extract the x outside this cos without using a cosine inverse function, you cannot directly solve it analytically using any method. So here you need to use some numerical techniques like bisection method, Newton-Raphson method, or in this case, like even a simple method like successive substitution. So let's see how this is done in Python. We import the math module to get the cosine function. Then we start with an initial guess value for x, that is 0. Then we establish a tolerance. We'll come to that later. Now we define an objective function which will return the cosine value of any x that we pass to that function. So this is where we define the governing equation of our model, right? So this is the equation which we need to solve. So we have defined that equation. Now the rest of the portion deals with how do we solve this equation. So we are iterating over a loop 100 times, and each time the concept of successive substitution is that we evaluate the objective function and the output will be returned back to the variable. Then in next iteration, that new value will be passed to the objective function and again passed back to the variable. So since cosine x is like a bounded function which will not explode over time, this is a elegant method to solve these simple systems. But for complex systems where we have more variables, more unknowns, more equations, and they have different behaviors, this type of simple models may not be sufficient. So you need to have more complex integrators, more complex numerical techniques to solve them, which makes the overall process much more tedious and error prone. And within that, like we defined a tolerance, so we cannot get an exact answer to this equation, but we have to see if the actual value and our solution are within a tolerance of 10 to the power minus 8, we will break the iteration and print the value. So by solving this, we will see that if x is defined in radians, we will see that 0.73908 radian is what we can get where x minus cosine of x equal to 0. You can verify this by using yourself in a calculator. But the key understanding that we need to take here is that the process of defining the equation and process of solving that equation are two different processes in a typical programming language like Python. Now let's see how this is done in Modelica. In Modelica, we start by defining a model. So anything that needs to be simulated in Modelica will come under the description of model and a model name, and we will complete it by calling the end model. Okay, end model name. Now within that we define a real variable, that is x. So unlike in Python, in Modelica, you need to define the type of the variable. So whether it is a real number, whether it is an integer, it is a Boolean, it is a string. This is not a dynamically typed language. So this is like a statically typed where you need to define the data type every time. After that, we call an equation section. So Modelica model has two sections. One is the variable or parameter sections where we define values. Now there is an equation section where we write the equations or where we define relationships. So it has two sets. So here we defined the variable x, and here we define the behavior of x or the relation of x with cosine of x by using the same equation. So Modelica has a math library and we can get the cosine function from there. Now the last part comes with annotation where we define an experiment starting with 0 time, stop time is 1, tolerance is 10 to the power minus 6, and interval of 0.002. So this particular equation has nothing to do with time, but an important thing that to be understood is that Modelica uses time as an implicit iterate. So regardless of whether your model is steady state or it is just a mathematical model having nothing to do with time, you have to iterate it over a time period to simulate. So by default, OpenModelica provides 0 to 1 second as a time interval, which can be modified anytime. Then the tolerances and the interval, time interval, like how many iterations to run, is also handled accordingly. So by running this in Modelica, you will get the value of the solution as 0.73908513. Here it is 85128 something. So if you look at the initial part, like we got the exact solution without having to worry about how the algorithm solved it. So that is happening behind the screen. We only had to define the equation. It's a good thing that Modelica can solve equations, but why is it relevant in solving physical problems or engineering problems? How do we convert a simple phenomena that's happening around us into a system of equations that can be solved using Modelica? Let's attempt this question by taking a very simple example. You're drinking coffee on a comfortable winter morning in your home. Somebody rang the doorbell, you have to go attend that person. It may take like 5 to 10 minutes of time. So you want to know whether your coffee will still be warm enough once you come back, or what will be the temperature of coffee once you come back. And you want to model it using equations in physics. So before we jump into equations, we want to understand what phenomena happens here by the time I'm gone. In that 10 minute, what is happening? So there is coffee at some temperature called T1, and there is ambient air that is flowing around it with a temperature T2. So if I say that my temperature of coffee was 80 degrees Celsius at the start and my air was at 20 degrees Celsius, so there is a temperature difference. And that temperature difference will drive the flow of heat from the coffee to the air. So that is my driving force. Now, what is being transferred from where to where? Heat energy is being transferred from warm temperature coffee to colder temperature air. So that is our flow of parameter here. Now, what are the elements that resist this flow? So there is a cup which is mostly made of ceramic or glass, which has a thermal conductivity. So for a given temperature difference, it can only allow the flow of certain amount of heat. So that equation is governed by conduction. Also, we have some phenomena happening at the top where coffee is directly exposed to air and the air is exposed to the mug. So here both cases like we have some convection. To put it little more formally, we can say that there is convection happening between coffee and air on the top surface. There is a sequential process like series process of coffee, then the inner wall, then the inner wall, like the wall of the mug is happening here. Then we have one more resistance of the outer surface. Then we have air. So this is a nested system of like internal convection, then conduction, then external convection from coffee to mug to the air. So two ways heat is getting lost from the uh, coffee. Then as a result, the temperature of the coffee will start decreasing because only if you have the heat energy, it can sustain that temperature. But before we model this into equations, we need to keep some assumptions and understand that we are not modeling the full reality as it is, but we are simplifying it only to solve some of the questions that we have. So we are taking that coffee has a uniform temperature, that we are not accounting for the stirring effects or the internal convections that's happening within the coffee. And we assume that across this surface, the heat transfer coefficient is a constant. We are not solving it based on the natural convection equations and Grashof number and so on, but we are assuming like a constant heat transfer. Now the initial temperature of the coffee is known. As we wrote earlier, let's assume it's 80 degrees C. Now the air temperature, this is the initial temperature, but it can vary over time. Now on the air side, the air temperature remains constant, let's say 20 degrees C throughout the time. So this is not an unknown. This is a known value that air will be always at 20 degrees Celsius. That we are taking an assumption. Now, this bottom phase where the mug is connected with the teapot and then the table and so on, that part of heat loss is ignored. We are not accounting that. Then to simplify the conduction equation to use the Cartesian coordinates instead of radial coordinates, we are assuming that there is constant surface area on inner wall and outer wall of the coffee mug. and there is no coffee that is getting evaporated and mixed with air. So there is no mass transfer happening. It's purely a heat transfer problem. So with these assumptions, like we have come up to our governing principles, which can be modeled as a set of 6 governing equations. The first one states it's a differential equation where we have a derivative term of T coffee as the temperature of coffee with respect to time. And it says that the rate of change of coffee temperature is equal to the heat energy lost from it. It is proportional to the heat energy lost from it. And that constant of proportionality is your specific heat capacity and mass. Now the total heat loss is a sum of the heat lost through the side faces and heat loss to the top faces. The top phase can be modeled by using the Newton's law of cooling, using the convection heat transfer coefficient, area on the top surface, and T coffee minus T air temperature difference. The remaining 3 equations solve the conduction plus convection problem, which is happening on the side faces. We hit the coffee with the internal wall of the mug, then conducts through the external wall, then again convects to the ambient air. So these 3 equations, we have altogether 6 equations that needs to be solved. Now let's see how many things we need to solve. We do not know the time evolution of the tea coffee. So this is one variable that needs to be solved. Then we do not know what is the Q total. We do not know that. Now again, if you don't know the Q total, parallelly we do not know what is the Q side and Q top. So we have 4 unknowns here. Then we have T coffee is already accounted. T air is a non-value, so we don't have to solve. But we need to know what is the internal wall temperature and external wall temperature of the mug. So we have 1, 2, 3, 4, 5, 6 unknowns and 6 equations. So this is a balanced system that can be solved. Now there are additional equations that require for area calculations or the heat transfer coefficients that are currently omitted because to keep the simplicity of this explanation, we can explore them further in upcoming sessions. So this would have given you a basic idea of how a simple physical phenomena of an everyday experience can be converted into a system of equations to understand the behavior of that system. We will explore this further by taking practical examples in upcoming sessions. But before that, I wanted to give a very brief and high-level introduction of how you can set up Open Modelica in your system and what are the key aspects of it. So let's get there. Open Modelica has mainly 4 components. That is the Open Modelica connection editor or called OM edit. Then OM shell where you can execute command line operations for running and simulating the Open Modelica models. Open Modelica notebook is a Jupyter notebook style notebook for building of Modelica models where you can do documentation plus modeling together in an interactive way. Then Open Modelica shell terminal gives you the command line arguments of your simulation execution, maybe like log asserts or debug reports or error messages, whatever is coming from the simulation can be shown in the Open Modelica shell terminal. Now, Open Modelica interface, the connection editor interface looks something like this, where you have a side panel with some library components. We will get to them in more detail. And we have a graphical window where we can drag and drop components from the library and connect them to build our systems. And we have a parallel text-based system which is synced with the graphical system. So once you drag in components, it will automatically generate the code required for that. So this can be based on how we are modeling, like we can switch between these two seamlessly and then complete our model. Let's take a quick look at their official website and see what it is offering. So in the home page, you can see that it gives a brief introduction, the version release, some video tutorials, and it has a cross-platform support for Windows, Linux, Mac. And Mac, we actually need a virtual system to run. It's not natively supported. It's recently discontinued. And there are some good tutorials that you can find. One is that tutorial set by Dr. Michael Tiller, which is called the Modelica by example. Link it to the description also. So you can get it from the mbe.modelica.university website. This is pretty interesting and you can download. This will roughly take about like 1.5 gigabytes of space if you download the official release. I will highly recommend to stick with official release so that it will be stable and you won't end up with random convergence issues or bugs in that. So it's pretty straightforward. You can download depending on your platform. You can get the instructions here. If you're in Linux, you can see how you can set up in Linux. You can download the tarballs, or you can configure it using command line arguments. So it's pretty straightforward process. I'm not going into details of that, but feel free to explore these websites and understand further and let me know your comments in the comment section. So with that, we are reaching the end of today's session. In our next session, we will talk about more detail about the basic syntax of a Modelica language. Then we will see how we can set up, how we can start, stop, step size, and tolerance values can be controlled. Then all this will be done using a physical example. So we will understand a little bit about how to have physical types like temperatures, pressures, etc. in Modelica, like how we can define them as variables. And then we will build a very simple transient lumped context model in Modelica. So this will give us a confidence to user on building a very simple model from scratch. Then we will explore further in the upcoming sessions. So see you again in next session. Happy modeling. Thank you.